we're especially going to emphasize the explanations here, because it won't be as obvious. Okay, so you did a nice job on the warm-up. All of these were either geometric or arithmetic, so it's nice, right? We know everything about the situation if it's geometric or arithmetic. We started talking just a little bit after the quiz yesterday about what would happen if we have a series that is neither of those things. So I'll just pull up this last slide that we were working on here. We talked about the nth term test for divergence, which is the first test on your blue sheet. And today we want to see if we can go through as many of the others as possible here. But just to recap, right? Like I said, if it's arithmetic or geometric, we know everything about it. We can write the explicit rule. If it's geometric, we love geometric series, right? Infinite geometric series, we know the conditions under which a geometric series converges or diverges. And if it converges, we can always say what the sum is. This is beautiful. And not always possible, not always easy, right, for a generic series. So we started looking at this example yesterday. We said, hey, here's one that is certifiably not arithmetic nor geometric. But still, can we say something about whether it converges or diverges, this infinite series? And we said, yeah, the nth term test is maybe one of our first lines of defense. This one diverges. And again, just to emphasize and underscore this, because everyone makes this mistake, it seems like. If the terms of a series do approach zero, then we have this tremendous conclusion. Oh, wait, no, we don't, right? We have to further test, right? It's not like, and the prime example of that will be the following series on the next slide. Okay? Introducing, are you ready? Some of the most important series, the harmonic series, okay? There's a cute graphic to inspire you. Ignore the box for a second. This is in fact, this first one is right here. I'll list a couple ones. This is usually what is referred to as the harmonic series right here. 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4. What's the rule? If n is 1 here, n2, n equals 3, what's the rule? It's just 1 over n. Nice simple rule. And this provides the first and easy counterexample to the nth term test. In general, you might ask about 1 over n to some power, p. By the way, this box is reproduced in all of its glory on your blue sheet. We're moving down the sheet here. We know about the nth term test. Number 2 was the geometric series test. We're good at that. The p series test is the one we have right here. So in general, this is called the harmonic series right here, but these are also interesting series for us as well. 1 over n to some other power besides 1. So this is the startling result here, right here. So let's look some more about at this series. 1 over n, right? The sum 1 over n as n goes from 1 to infinity. Again, let's think about the nth term test for a second and realize that it doesn't help us. Okay, the terms of this series 1 over n. The terms themselves, forget the sum for a second. The terms go to 0, don't they? I mean, 1 over x. What's the horizontal asymptote? 0, right? The terms forever get closer and closer, arbitrarily close to 0. The sum, though, diverges. Is that right? If we had time, I might actually plot the partial sums on the calculator to show you how it slowly diverges. It's hard to tell. You might think, is there a horizontal asymptote above that? There isn't. Any sum you think that this doesn't go above? Name a number. 10. I don't think this ever gets bigger than 10. I can find you a place, a number of terms that you need to add up that will make it bigger than 10. Okay, well maybe just guessed wrong. Maybe it's actually 12. Maybe it's 100. This never goes above 100. No, I can find you a number of terms after which this sum will exceed 100. It's very slow growth, though. It's on the order of, it's like logarithmic growth. So it's very slow growth. It might take me a million terms, right? But I can show you a place where it goes above whatever your number is. That's not true of 1 over n squared, though, amazingly. And this seems very arbitrary to us right now. And I'm giving this fact to you without proof. The easiest proof of these facts comes from calculus. And so all of these get done pretty quickly, proved nicely, with a little bit of calculus you'll learn a year from now. But there are some nice proofs that the harmonic series, the plain old harmonic series, diverges, and and those I have a whole bunch of those linked to on my blog if you want to go, go look them up. There's an article that has like 12 proofs of this fact or something like that. And there are some cute ones that don't involve calculus, so it's fun. We can do one. Yeah, Andrew. Yeah, but in a very, kind of, not really. Yeah. Not quite. It's a continuous function though, right? It's 1 over x for continuous values, and we're talking about area under a curve, or volume and surface area, things like that. Yeah. Yeah, it's complicated, right? So the volume when you do, yeah, we'll talk. Yeah, it's complicated. Yeah, I can fully explain it to you, but I don't want to. It also involves, if you want the full explanation, it involves calculus. But it is true. If you haven't heard of Gabriel's horn, you can look it up. It's a infinite. It's a horn-shaped 3D solid that has an infinite amount of that has a finite amount of volume, but an infinite surface area. How can that be? It's kind of a little bit of a paradox. It's not really a paradox to mathematicians, but so this one converges, and amazingly. Now, typically, we don't know the sum of a series. If it's geometric, we do. But in general, today, as we move forward, if a series is not geometric, you're going to just say whether it converges or diverges, right? I'm not going to also ask you. Our question, in fact, will always be, does this converge or diverge? If it converges, find the sum if possible, right? And by if possible, I mean if it's geometric, right? But generally, we don't have a way of summing infinite series that's nice. It's like a very, very large problem in mathematics, actually. It's like it's a big question. It takes a lot of trickery to figure out that this series, for instance, 1 over n squared, does have a finite sum, and it is pi squared over 6. Amazing. Euler, the genius, is the one who showed that. Leonard Euler is the man. It is. It's on the poster over there. And in fact, all of the nice 1 over n to some positive integer power have been summed. And they all have that kind of form, like pi squared over 6. But anyway, that's kind of an anecdote. I don't need you to know that. It's just interesting, isn't it? There you go. So the point is, if p is 2, or p is 3, or p is 4, or p is 4.5, that's also fine, converges. But if p is 1, or a number less than 1, like here we have 1 over n to the 1/2, right? Then it diverges. So just to be clear, right? 1 over n to the 1.1. Slowly, but it converges. This sum is a convergent sum, 1 over 1.1. Right, so less than or equal to 1, if p is less than or equal to 1, it diverges. Otherwise, it converges, right? So, okay? But again, let's think about the nth term test. Let's go back to the previous page for a second. That's all right. It's so good. I'm not hurt. All of these, no matter what p is, all of them, the terms go to 0, right? Regardless of what p is. Yes, provided p is positive. Okay? They all go to 0. The terms go to 0, right? So the nth term test has nothing to say about this, right? This is a perfect example of why the nth term test is good for some things, but not this, right? And there's a link you can click on when you look at this PowerPoint later another time. Or you can just search online for it. If p is negative, then of course it diverges, right? Yeah. Yeah. There's an interesting question. In fact, you might ask, what would happen if p is a complex number, right? And then you get something called the Riemann Zeta function. It's a very important function in mathematics. And the question of whether it converges or not, and where its zeros are, is a famous problem. You can earn $1 million, in fact, if you solve it. So it's one of the millennium problems. Huh? Yeah, I just haven't told them about it. I put it on I put it under my bed and on a piece of paper. The Riemann hypothesis is that. So when I die though someday, you can.
Okay.
Yeah, you can catch it. All right. Actually, the Riemann hypothesis is what Miss Petulante's husband works on all the time. That's like just what he does. He just works on that problem. He's a professor at somewhere. Where is he? I don't know. All right, let's look at the direct comparison test. That's the next one down the list here. So we talked about the insert test. We talked about the geometric series test. We talked about the P-series, when they converge and when they diverge. So let's think about the direct comparison test. And this will, we're doing this in the right order, I think, because this will use heavily our results from the previous stuff we've been doing. All right, so this should make intuitive sense. Let's just look at the first sentence, and then we'll look at the second sentence. So if you have a series, say I own a series in my possession that I know to be convergent, like I've told you, we've proven it, mathematicians through the centuries have proven that the series I have, like, I don't know, series 1 over n squared or something. I have a series in my possession that we all know and agree is convergent. You know, you come up to me with some unknown series. We don't know yet whether it converges or diverges. But your series is term by term. Each term, your first term, is less than my first term. Your second term is less than my second term. Your third term is less than my second term. Well, mine converges, and yours is always smaller than mine. So what must be true about yours? Well, it must converge too, right? And I think just that intuition is enough to understand why this is kind of a pretty reasonable thing to appeal to. The second part is, if I have a known divergent series, I'm holding in my possession a series we all know diverges. And then you come to me with your unknown crazy series that we're not sure about yet. And term by term, your terms are each greater than, pairwise, right? Greater than my terms. Well, then it should make sense that yours diverges, right? Mine diverges, and yours is always bigger than mine. So, of course, yours diverges. So those are the two parts of this test. You don't want to get them confused, right? I have a convergent series, and you have a series that's bigger than mine. I don't know what to tell you, right? We can't mix those two. But this, again, it's kind of an appeal to intuition. It should kind of make sense why this is true. So, for instance, this one here, 1 over n to the 4th plus 3. Before we do anything else, we should identify this as looking kind of like one of the things on the previous slide, right? You know, this kind of has a feel, and you kind of have a feel too as a mature mathematician now, that this has the kind of the same behavior as 1 over n to the 4th, doesn't it? The plus 3 is really not doing too much for us. So my thought is that this is maybe going to behave something like 1 over n to the 4th, the sum, right? Which we know something about. This is a series which we know. Which one? Converges or diverges? Based on the previous slide. Yeah, this is this is p equals 4, which is greater than 1, so this converges. So we're thinking that maybe this one does too. Okay, so what does the direct comparison test say? Well, we're hoping maybe that this is, for any n greater than or equal to 1, that this is always less than this. Is that true? That is, that expression right there is always greater than this expression here. Is that true? Can you convince yourself that that's true? If you want like a formal argument, this is in fact always greater than this. Here might be how it goes, right? We don't need to do this each time, but certainly that's true. Do you agree? Okay. And this is true. Do you agree? Property of inequalities that maybe you didn't know. You can add whatever you like, any positive number, to the side that's greater, right? Isn't that fair? This is still true. And then now I'm going to divide both sides by each side, right? So over here I'm going to have an n to the 4th. And n is positive, so I'm allowed to do this, okay? And non-zero. Okay? And there we've just proved it, right? From very first principles. Yeah, I think this is kind of silly, right? I mean, as I said, you probably don't need to do this. I think once we've done this, you understand, though. You know, bigger denominator, smaller fraction. Okay, yeah.
I do want to show that.
Yeah, you don't need to show this, is what I'm saying. We'll be a little bit loose with this. And I'm not going to give you ones that are like super hard to prove necessarily. Hopefully it'll be somewhat clear like this. All right, so since, here's what I actually want you to write. Okay, so actually write this. or something like it. Since 1 over n to the fourth, the series from 1 to infinity, converges, and let's say y, because that's p equals 4, which is greater than 1. And 1 over n to the fourth is always greater than or equal to 1 over n to the fourth plus 3 for all n greater than or equal to 1. The series we're looking at must converge to by direct comparison. Right. Is that fair? What does it converge to? I don't know. Right? I don't know. We could approximate it to 10 decimal places if you like, by adding up the first 10,000 terms or something. But I don't know. Is that okay? That's how the direct comparison test works. This is, there are other things that could happen here. Let me show you another one. I don't think we'll do this. Actually, I don't think we'll skip this one, but just say out loud what this one would be too. I think this is maybe not worth doing, but a little different in feel, but what do you think? Converges or diverges? What does it feel like? What is it on the order of? What is it? Yeah, which one would you maybe compare this to? Yeah, 1 over n to the fifth maybe, and you'd want to maybe prove that this is less than that, which is not too hard to convince yourself of again. All right, so this does converge. Exercise left for the reader. Okay, but prove it. Like actually say, you could actually justify this stuff. Okay. All right, and then down here, what's going on down here? And 9n to the negative 2/3. What do you say? Yeah, I think we have a hunch that diverges. What does this one feel like? This is kind of similar to one of the, like I said, we're kind of always using these P series as a reference. You could use other series, but the P series ones are really nice, especially the kinds of awkward.
I guess the 1 over n to 2/3.
Yeah. Yeah, so this is 1 over n to the 2/3, which diverges, right? Because p is 2/3. So you could use, we could actually use the direct comparison test here. So let's do that, and then maybe it's overkill too, but this is 9 times that. So since 1 over n to the 2/3, that series diverges because p is 2/3, which is less than or equal to 1. And 9 over n to the 2/3 is always greater than or equal to 1 over n to the 2/3. So must our series diverge. So that's one way to justify. That'll be fine. But it should also be clear. Maybe the direct comparison test is a little bit overkill here. Certainly, using properties of summation, right? You can pull this 9 out, and then you get 9 times this, and this diverges. So 9 times something that diverges also still diverges. You couldn't really do that on the last example, right? Because there's like a plus something in it on the bottom, but you're welcome to do these in multiple ways. So they're not always one way to do it. Questions on that? one thing that should still be kind of left in our mind, though, is like, what happens if I give you, you know, well, one like this is the one we're going to do now, right? This is my next example. What happens if we give you 1 over n to the 4th minus 3? Your first thought is a good one, isn't it? This is like 1 over n to the 4th, isn't it? But the problem is, using direct comparison, even though direct comparison has this beautiful, nice kind of picture in our mind. Oh yeah, less than a conversion. But the problem with this one is what? It's always greater than 1 over n to the 4th. The direct comparison is not, though beautiful, is not very powerful, actually. Because if this is a plus, it works, but if this is a minus, it doesn't work? That's kind of dumb, right? So it's not that powerful. This test will work on anything that direct comparison tests worked on, right? But it is a little maybe more cumbersome and a little harder to unpack. So this is the next one on your sheet. It is number 5 on your sheet. It should be reproduced exactly on your sheet, just like that. It's called a limit comparison test. You have a feeling, even though you're like, who cares if it's a minus or plus, right? Who cares? This still has the same kind of growth rate as 1 over n to the 4th, right? You have that mathematical maturity to know that, I think, right? That this has kind of grows at the same rate as 1 over n to the 4th. The minus 3 plus 3 doesn't matter out of infinity. All right, so this is us formalizing that. Okay, you think this acts like 1 over n to the 4th? Awesome. That is the correct mathematical intuition. Good job. So what this says, the limit comparison test says, if indeed these have the same growth rate, or that they're on the same order, you might say, then if you stack them, that is 1 over n to the 4th, divided by 1 over n to the 4th minus 3, right? If you do this thing, divided by this thing, or vice versa, then when you take the limit as n goes to infinity, you will get a constant. If indeed they're growing at the same rate, okay? If they're not growing at the same rate, let's consider what might happen. If an is growing faster than bn, that's the numerator, you go back to your rational functions knowledge. If the numerator is growing faster than the denominator, then what does this tend toward? Infinity, right? If the top is growing faster than the bottom, then we're headed off to infinity. What if the bottom is growing faster? We're headed towards 0. So if we get 0 or infinity, then that says, that kind of proves nothing for us, right? We would love to, if we have really chosen to series that grow at the same rate, then when we do this, we stack them, and we take the limit, we should get a constant, right? And actually it can be negative too, but the point is we don't want to get 0, and we don't want to get infinity, because if we do, that's actually not a problem. We just have to do the test again, and maybe we pick the wrong thing. Yeah? Okay, so this is how this would work, right? We'd say since, and again I want to kind of explain what's going on, since the limit as n goes to infinity of, and we can stack these in either order, 1 over n to the 4th divided by 1 over n to the 4th minus 3 is equal to the limit as, and let's actually do some algebra here, n to the 4th minus 3 over n to the 4th, which equals what? Yeah, you guys comfortable evaluating the limit, right? Using rational function technology from first semester? Very good, wonderful. Since the limit of this divided by this is 1, and 1 is a number in the interval 0, the open interval 0 to infinity, and, one more and, 1 over n to the 4th, the sum, converges because p is 4. So must our series. By LCT, by the limit comparison test, right? Is this okay? Like I said, if you stack these in either order, you'll get a constant. You're doing this right. Okay? Again, what would happen if you picked 1 over n cubed? Because I don't know, because you're dense.
You get 0.
Yeah, if we put 1 over n cubed, this would be n cubed here, not n to the 4th. And what would we get?
Infinity.
We get infinity. If you stacked them the other way and you had 1, you'd get 0, right? So either way, that would be bad, and you'd be like, okay. It's not a problem, it just didn't tell me anything. Go back and try something else. Right? Why'd you pick 1 over n to the cube? 1 over n cubed. That's dumb. Don't do that. Well, maybe it's not dumb. I mean, here it's pretty obvious, I think, that it's 1 over n to the 4th, right? That we should be comparing this to. So I'm going to show you one in a second that's not so obvious what thing it's growing like. Yeah.
Wait, does it have to be a plus or constant?
No, not necessarily, actually. Yeah. So here's another example we're going to do. We're going to use the same technique, actually, to do this. And by the way, on each of these, we should still be kind of running through our other tests, right? Is this arithmetic? Is this geometric? Does the n-term test help here? You know, we can kind of ask those questions. And I'll just tell you, none of those things help. It's none of them, right? Okay, so we are going to use the comparison test, but the big task here is to think about what this grows like. Right? So we got to think this through a little bit, because this is not easy here. Out infinity, do you agree that, just from your knowledge of polynomial functions, that n cubed minus 1 just acts like n cubed, right? The minus 1 gets dominated out of infinity. If you're cubing 10 billion, then the fact that you also subtracted 1, neat, right? It's like, who cares? So I think, just based on my cavalier mathematical intuition that I just ran through with you, that this kind of acts like that, right? As if the minus 1 isn't there. Again, I'm just kind of feeling somewhat kind of the intuition too, but then I hear you say, but that's not a p-series. Or wait, maybe it is. Can you clean that up a little bit using rules of exponents? What do you think? Yeah, so this is n over n to the 3 over 2. Okay, but that's still not a p-series, though. Right? That's progress, though. Yeah, n to the first over n to the 3 has kind of wants to weigh in. Yeah, subtract exponents, and what do we get? Yeah, n to the negative half, which is 1 over n to the 1/2. Ah, now we're somewhere. I think, and this was not obvious when we first looked at this, was it? Not even a little bit. I think this grows like 1 over the square root of n. Cool. All right, now we're somewhere. And furthermore, my hunch is that then, of course, this diverges. That's my hunch. Okay. Not obvious. When you just first look at this, you're like, oh, this converges. Oh, this diverges. No, how would you know? You really do kind of have to think through what we just talked about, right?
Do you have to do the root test or do you
Yeah, we're going to do it.
do you do the direct test?
That's a good question. Is this...
Because negative 0 never terms be bigger.
Yeah, can we prove that this is always bigger than 1 over than that? Yeah, actually you could use either one here. Huh. Which would you like to do? I was going to use the limit comparison test, just because it's what you've just been doing. But here, we'll do the limit comparison test, but actually I think you're right. I think the direct comparison test actually might be easier here. We'll do the limit comparison test just to prove the point here. Because what if this was a plus, right? All right. So, in fact, here, let's change the problem just for fun. There we go. All right. Now you can't use the direct comparison test. All right. The limit as n goes to infinity of, oh really? Are we going to stack these things? Stack them in either order. 1 over n to the 1/2 over n over the n. All right. Finding this limit will be a little tricky, but we can do it. Let's try it. The limit is, if you flip this guy, we get this right on top. Right, multiply by the reciprocal, and on the bottom we'll get n to the 3/2. Right? Is that okay? If you remember, when you're dividing by something, you multiply by the reciprocal. So the denominator gets flipped, and on the top we'll have this, and on the bottom we'll have n times n to the 1/2. Is everyone okay with that? Are you sure? Jessica's right there with you? Okay. Alright. Matthias, this is good stuff, man. Here you go. Alright. So far, so good? We're going to pull another trick here. This is, let's use our rules of exponents kind of in reverse here this time. This is the square root of n cubed, isn't it? So I'm going to write this. Is that okay? Alright, and now what is the limit as n goes to infinity? Forget the square root. What's the limit? What happens to the thing inside the square root as n gets large? It goes to 1, doesn't it? So this goes to, I say, to the square root of 1, which is 1. Okay. And 1 is, again, a number not 0 and not infinity, so that's good. Since 1 over n to the 1/2, that series diverges. So does this series. Oh, by the way, this is interesting. Why does there have to be a 2 there? Riddle me that. We're all done. Good. Okay. So why does there have to be a 2 here? Just out of curiosity. Oh, actually, it doesn't matter now.
Oh, yeah, because those are minus.
Because I changed the problem. But why originally, in the way I had the problem formed, couldn't we start at 1? It was just, right, all these tests work just great, starting at some other point, right? If you can prove a series converges or diverges, starting at n equals 100 and beyond, then you've done it, haven't you? Because who cares? The first set of terms, no matter how many terms you capture, is finite, right? That's sum. So after that, if you have a convergent sum, so you can start at any value you like on these sums. It's not a problem. So anyway. So we can do it either way, +1 or -1. It'll be the same result. You're looking at this work here?
Yeah.
Okay, so you're good on this to here?
No.
Okay, yeah, so sorry. Yeah, let's maybe work it up here. So you get 1 over n to the 1/2 times the cube root of n, the square root of n cubed plus 1 over n. And then this is n to the 3/2, adding powers. Right, yeah. But let's say a little something about the ratio test. I'd love to say something about the ratio test. That'd be great. We'll have to clean up tomorrow a little bit, for sure, because the ratio test is a little bit intense, but we can at least start giving you the flavor. It's the last one on there. I just can't not say something about it. Okay, so here's the ratio test, again, produced in all of its perfect glory on your paper, too. But this is a pretty powerful test. And again, it kind of is helping us compare the growth rate of different things happening inside of a rule you might be looking at. So I'm gonna we'll explain a little bit and see if we can even do one example. Maybe that'd be great. So that's exactly right. If this kind of feels down here, doesn't it? Like we're talking about a geometric series. In fact, if you do this with a geometric series, what's the ratio between one term and the previous term for a geometric series? Well, it'll always be a constant, right? There's not, in fact, with a geometric series, there's no need to take this limit. No matter which 2 terms you choose, if it truly is geometric, you will always get the same number. It's not like we're taking a limit. But what the ratio test helps us see is that if you have a series that's not geometric, but out at infinity, when you do the ratio between the 100th and the 99th term, for instance, or when you do the ratio between the millionth and the 999,999th term, if that ratio is stabilizing out at infinity, it's not geometric, but out at infinity, it's acting like it's geometric, right? Does that make sense? And if that's true, if it's not geometric, but it's acting like it's geometric out at infinity, if this ratio between terms approaches some value, call it R, then the same things that you did with geometric series can be applied to something that's not geometric. Cool. So, for example, this is the series n over 2 to the n. Okay? The sum. And we'd like to test for whether this converges or not. Would be great to know. All right. So let's compute our R value. R is equal to the limit as n goes to infinity of the next term. What's the next term going to be? In the generic next term, it'll be n plus 1 over 2 to the n plus 1, right? And then the current term, which is n over 2 to the n. All right, so this is the next term, this is the current term. And if this was a geometric series, this would just come out to be a number always. We wouldn't have to take a limit. And when we do this, again, I'm going to pull that same trick. I'm going to do a little flip here. We get n plus 1 times 2 to the n on top when we flip. And we get n times 2 to the n plus 1 on the bottom. Rules of exponents tell me that this is 2 to the n times 2, isn't it? If you break that apart. So I can cancel these out, leaving just a 2 in the denominator. So we get n plus 1 over 2n. What's that? What is this limit? 1/2. So I didn't get to write the rest of this, right? But does this converge? It does. Because the limit between the ratio of terms is 1/2. It acts geometric. Okay, you can't leave it till you get the piece. This is the homework 3 addition. Tonight you're going to do this piece. So another, just half a homework. You've got a jet on the ground. You gotta bring your Red Bull. Sorry. You do it every day. I do this. We all have it. Because I told you so. For any p, for 1 over n to the p, right? It converges if p, if that p value is greater than 1. And it diverges. That was the p series test. Right? So 1 over n to p is diverges. P is or equal. Anybody else gone tomorrow who wants to work these? Alright, so tomorrow we're going to do this. And then Friday we're going to do this with the activity in class. So then you don't have to show me that necessarily. I'm not actually going to teach a lesson on Friday. It's like a discovery. Okay, so we're just going to do the next one. Yeah, I will probably heavily guide people when they get back. So, see how you do it. Yeah. Oh, no. All right. Here, you take all these. Yeah, take one of each of those. You heard what I said, Dad. So,